Welcome back to Securing Digital Democracy. Since computer scientists have had so many criticisms of electronic voting systems, some people have thought this was a very strange thing. What were these high-tech people thinking? Were they suddenly Luddites? But what computer scientists and researchers in the voting field know is that there are ways to use technology well and ways to use it poorly. That there are some things technology can do securely and some things that it's very hard to make technology do securely. In this lecture, our focus is going to be on some new ideas about how to use technology in the voting process in order to make it more secure. I'm going to introduce a series of technologies that have been developed by researchers in this field and give you an idea of what the future of technology in voting might look like. But before we begin, I'd like to talk for a few minutes about some of the criteria, some of the desirable properties for voting systems that people in voting research and voting practice talk about all the time. And when we're evaluating voting systems, both old ones and new ones, it's important to think about how well they meet these criteria. The first property, and probably the most abstract one and the one we talk about most, is the idea of transparency. People talk about the need for election transparency in relation to things like DRE voting machines. What we mean by transparency is the property that voters can observe and understand the election process. This is important for several reasons. Transparency allows voters to observe and thereby understand why their votes are being counted. It allows voters to understand what the rules are. It allows them to make sure that election officials are doing their jobs. For those reasons, we might propose a more full definition of transparency, and this one comes from Joe Hall, which is that a fully transparent election system supports accountability as well as public oversight, comprehension, and access to the entire voting process. Another extremely desirable property is what we call verifiability. Verifiability means that voters have some means to convince themselves, rationally speaking, that the election outcome is correct without having to just blindly trust that the technology is functioning correctly or that the election authorities are honest. An example of a voting system that has the verifiability property might be paper ballots where people are free to go and observe the counting process, because then the voter can directly convince themselves with their senses that the outcome is correct. On the other hand, a system that is not verifiable is paperless DREs, because in a paperless DRE, the only count of the votes is happening by black box software in a way that people can't observe and where people just have to have faith that the software is correct. Another important property is auditability. And that means that the system has some way that it can be manually checked after the election to ensure that the votes have been counted properly. Optical scan voting has this property because we have a set of paper ballots that we can spot check or recount to make sure that the totals are correct. I'll talk more about auditing elections later in this lecture. Finally, a property that has been defined with respect to software used in the voting process is an idea called software independence. And this is an idea that was coined by this man, Ron Rivest, who, for those security nerds in the audience, is an American cryptographer who is the R in the RSA crypto system. Ron's idea is that a voting system is software independent if an undetected change or error in the software cannot possibly cause an undetectable change or error in an election outcome. Now, this is a really powerful idea because it allows us to distinguish between systems where we have no choice but to blindly trust that the software is secure and correct, and systems where we have some means of catching any problems or cheating attempts that the software might be making. And examples of systems that provide this property of software independence are optical scan systems and DREs with paper trails, so long as we are catching any problems by auditing those paper ballots or paper trails after the election. So I'll talk a little bit more about software independence when we talk about auditing. So those are some of the most desirable properties in elections. Now let's see some ways that systems can provide these. When there's a close election, something we often see afterwards is a scene like this, a manual recount of the ballots cast in the election. And recounts like this are both an important security feature and a potential opportunity to employ technology to make the process better. A recount is an important security feature because in any kind of counting process, we're likely to see some fraction of votes be counted in error. This is true no matter what the voting technology. It's just in a complex process involving thousands of locations. Some votes are going to be misplaced, some are going to be misinterpreted, some are going to be lost. And a manual recount is an opportunity to check up on the whole process. Some voting systems, like DREs, provide very limited opportunities for a recount. If there's a recount in a place involving DREs, what election officials are actually doing is just pressing the print button again. Maybe they're going to check their arithmetic, adding up the totals from the different machines, but there's no opportunity to actually go into the machine and evaluate each ballot individually, since the software in the machine, if it was dishonest, will have changed all of the records. The most time-consuming audits, but also recounts rather, but also the most thorough, are ones that are involving paper ballots. Recounts of paper ballots can be time-consuming and costly. And so there are rules in place about when they occur. Most states have a law that invokes a mandatory recount of all the ballots in the election if the margin of victory is smaller than a certain predetermined threshold. Also, in most jurisdictions, candidates or sometimes voters can request a recount if they're willing to pay for it. Usually the state will refund the cost of the recount in the event that the election outcome changes, but it's still a big gamble for whoever's making the request. That cost can be very high when it comes to recounting paper ballots. Figures from different sources vary, and it depends a bit on what you're taking into account. But the cost to manually recount a paper ballot can be anywhere from tens of cents to more than $1. And in a large election, that can very quickly add up. So the cost can be prohibitive to manual recounts in large jurisdictions. Now, a related topic to recounting is the idea of post-election auditing, which involves very much the same process of going back and having people review physical records of some of the votes. Now, let me explain why post-election audits are an extremely valuable security feature. So, in a system that provides auditability, like a precinct count optical scan voting system, we end the election with two sets of records. We have a set of paper ballots, which are slow and expensive to recount manually, but are verified by the voter. So in some ways, these are the strongest evidence we have of the voter's intent. On the other hand, we also have a computer record, an electronic record in a memory card, say. This is fast and easy to count because it's a computer record, but it's not verified by the voter. This kind of redundancy between different records, which, as I explained earlier in the course, also have very different security properties and failure modes, offers us a chance to get much greater security for the whole system. However, this redundancy is only useful if we check both records to make sure they agree. And checking these records for consistency is the role of a manual audit. So a manual audit is a process that can be conducted after the election but before the final results are declared. And it involves spot checking the ballots to make sure that the computer records and the paper records agree. Unlike a recount, which usually takes place throughout the entire jurisdiction and involves all the ballots, a post-election audit usually involves selecting a random subset of all of the precincts and then just counting the pieces of paper in those precincts to check whether they agree or disagree with the computer records in those places. If there's a disagreement, we can elevate to a recount of all the ballots across the entire jurisdiction. One important criteria for this, though, is that the places that we're going to audit have to be picked randomly. We can't announce in advance where the audits are going to be held, or anyone who was going to commit fraud would just make sure the fraud was committed in places that weren't going to be audited. Furthermore, there have been documented cases where election officials, in order to avoid a wider recount, went and checked the ballots in certain jurisdictions beforehand in secret and then announced that those were the places that were going to be audited after they knew that there weren't any discrepancies that were going to be revealed. Those kinds of shenanigans can be avoided if we carefully come up with procedures for randomly selecting where the audit locations will be. One way to do this that's frequently talked about is to use stock market closing prices on the day before the audit is going to be held. That way, it's very hard to predict or manipulate which set of places is going to be subject to the audit. Another question is, how much do we need to audit? How many precincts, for instance? And the standard practice is to use a fixed fraction of the precincts, say 10% of them, selected at random. This has some problems, though. A better alternative would be to fix the level of statistical confidence we're shooting for. Say we want to audit enough that we'll be 99% confident that the outcome is correct. If we just audit a fixed fraction of precincts, we're either going to be counting too many votes or not enough votes to reach a given target level of confidence, because the level of confidence we get from auditing, say, 10% of precincts depends on the size of those precincts, the number of votes, the margin of victory, and other factors like that. So the recommended practice is to fix a level of confidence and then audit until you get to it. This idea of picking a level of confidence leads to the idea of a statistical risk-limiting audit. That is, you audit until you can establish with your given level of confidence that hand-counting all of the paper records would yield the same winner as the electronic tally. A couple of states have implemented pilot programs with statistical risk-limiting audits, and I'm hoping that the majority of states follow suit in the near future. So let me give you an example of an audit that we can use to see how statistical risk-limiting audits might work and ways that technology can make them much more efficient. So in our example, we have candidates Alice and Bob. And Alice has gotten 55% of the votes, and Bob has gotten 45%. What we want to do in this audit is reject the hypothesis that more than 5% of ballots differ between the paper and electronic records. So we're going to pick some precincts. In order to get 95% confidence, let's say we're going to have to pick 60 precincts and hand count the ballots in those places. The problem with this is going to be the cost. If those precincts are large, auditing 60 precincts might cost, say, $100,000. We'll see an example that can reduce these figures in a few minutes. So there's an alternative approach that can make these costs much lower. So rather than picking whole precincts and auditing there, which is the standard practice today, we could try to pick individual ballots and just make sure that those individual ballots agree between the paper and electronic records. Let me give you some intuition for why this is much more efficient. On the left here you see 100 marbles. Let's say those are standing in for precincts. 10% of the marbles are blue, which are precincts where error or fraud occurred. On the right, you see 6,300 beads, again with 10% of them blue. These represent individual ballots and ballots with error or fraud. So if we sample 10% from each of these sets of things, in which case are we going to have a greater likelihood of finding a blue unit? In which case is our 10% audit more likely to turn up fraud? So the question is, how large a sample do we need to draw from each of them to reach our given statistical confidence level? And the sample you're going to have to draw from the marbles is going to be a much higher percentage than the sample you have to draw from the beads. So if we apply this intuition to auditing and come back to our example, we can see that if we move from auditing precincts to auditing ballots, we can drastically reduce the cost. Because using a ballot-based audit, we might only have to look at 60 ballots from across the entire jurisdiction. This would reduce the cost from $100,000 to way less than $1,000. So what's the problem, though, with the idea of a ballot-based audit, of sampling individual ballots to get to our statistical level of confidence? The problem is that we need some way to match records from the computers, from the electronic count, to individual ballots. You have to have two things that allegedly agree, according to the computers, to check that they actually do. One way to get this would be to have serial numbers printed on all of the ballots and to record those along with the votes that the machine thinks are on each ballot. But this creates a privacy problem. It's difficult to establish this correspondence in a way that doesn't compromise the secret ballot. So now I'm going to show you a new idea that came out of some of my earlier research that is one way we can perform an audit with a more efficient ballot-based way without compromising the secret ballot. And this is very interesting because it involves a way that we can use machines in the process without having to trust them. So what we begin with is the results from the election. Let's say we have a set of paper ballots and a set of computer totals. So this is our starting point for the audit. And what we want to do is establish that the paper ballots and the computer totals are in agreement. So the first thing we're going to do is check that the electronic records match the paper records, and we'll do this using something I call a recount machine. This could be an off-the-shelf commercial scanner hooked up to a PC running special software. And its job is to scan in all the ballots and produce two sets of records as a result. First, it's going to produce a computer file that has the votes from each ballot individually, together with a new number, the ballot number. Second, it's going to print on each of the ballots as it's being scanned that same ballot number. So it's going to number the ballots and produce a computer record that has for each ballot number the votes that were recorded there. Now we're doing this as a separate process after original voting because that way the ballots have already been shuffled, the order has been lost, privacy has been protected. But if we scan them a second time after the real count, now we have an opportunity to enumerate them and to produce this kind of record. So we'll take that electronic record from the recount machine and we'll compare it to the records from the initial count. If there's any mismatch, we need to do a manual recount. But if the records agree, we're good, right? Well, actually, we have one problem, which is that we need a way to know that the recount machine wasn't lying to us, that it was more honest. Why should we blindly trust that machine if we weren't going to trust the optical scanners or whatever machines produced the initial count? But using ballot-based auditing measures, we can verify that it's behaving correctly. So the second step is that we're going to audit the recount machine by selecting random ballots from the pile for human inspection. So we actually select records, then pull the corresponding ballots out of the pile and make sure that they agree with the records that the recount machine produced for those same ballots. So looking at this whole process, we can see that there are really two steps. We're going to do a machine recount coupled with a ballot-based manual audit. So this is really neat to me because this is a way we can use a machine in the election process without having to trust it at all, since we can manually verify that it was behaving honestly. This kind of technology can significantly reduce the amount of work we have to do to perform a post-election audit. Let's take as an example the 2006 Virginia U.S. Senate race. There was a 0.3% margin of victory. So this is a very close election, and if we want to establish with 99% confidence that the result is correct, with a traditional precinct-based audit, we'd have to have people look at more than 1 million ballots. With a machine-assisted audit, we can reduce that number to just a bit more than 2,000 ballots. So this is an incredible savings in terms of the amount of time and money and human effort that has to go into the process. And it comes without having to trust the technology at all. Other researchers have spent a lot of time trying to think of efficient rules for figuring out how many ballots have to be audited using ballot-based audits like this, and have come up with heuristics that are really smart. It turns out that if you look at the contents of the ballot, for instance, you can reduce the number even further. These kinds of reductions are being coupled with very easy-to-use heuristics for determining that number of ballots you have to look at. So all of this work is going into trying to make sure that the procedures are easy for election officials to follow and simple to write into election system procedures. So I hope that ballot-based audits like this and routine post-election auditing will become a much bigger part of election practice in the future. This is especially important because it's part of what's probably the gold standard in election technology today. Precinct count optical scanned ballots, paper ballots scanned at the polling place, coupled with a mandatory risk-limiting post-election audit that occurs before the election results are declared. This is about as good as we know how to do in terms of all of the properties we want from elections based on available technology today. What if we could use technology to fundamentally change the way that we provide election security, to make elections that were more secure, more verifiable, with higher voter confidence than ever before? This is the promise that is driving a very active field of research in computer science today into what are called end-to-end verifiable voting systems. So as a voter today, you don't really know what's happening behind the curtain. Even if the process is observable, few voters will actually be there to watch it. You'll probably have to trust other people to be there making sure that everything's being done right. Often you don't even get to choose who those people are. So there's always going to be some room for doubt in the back of your mind that your vote was counted correctly. But let's say we wanted to have some way to dispel this doubt. We actually wanted to have a system that could give every voter some notion of verifiability. So this is what end-to-end or E-to-E voter verifiability is all about. In an E-to-E system, as a voter, you can be sure that your vote is cast as you intended, that your vote is counted as you cast it, and that all votes are counted as cast. And this isn't just in principle. I actually mean that you can verify that your personal vote was counted the way you cast it. So let me give you a thought experiment to prove that this is at least possible in principle. So what if our voting system involved the following? We were going to collect everyone's ballot, and then the next day in the newspaper, we're going to print everyone's name and address together with how they voted. So we can see that this provides these properties. You can verify that your vote was cast the way you intended. You can verify it was counted the way you cast it. It's going to be possible for every voter to do that, so you can be sure that if there are significant discrepancies, they're going to be caught. But there's one major problem with this. It's not a secret ballot. So the question is, can we provide a system that has all of these verifiability properties, but also ensures that no voter can demonstrate how he or she voted to a third party, that provides a strong notion of ballot secrecy. Many researchers think the answer is yes. We can provide a system that is both verifiable and maintains the secret ballot. And the way that they propose to do this is by introducing computer cryptography to the process. So here's how the voting process might look to a voter using an E-to-E verifiable voting system. They'd vote normally using the whatever process they use, be it a DRE or an OpScan paper ballot. But at the end of the process, they'd get a verifiable receipt, maybe something that looks like this. So the receipt is something you can take home with you, but it provides a secret ballot because it doesn't show how you voted. Instead, you get a long sequence of letters and digits or a barcode. Either of these is essentially a computer record of your vote that's been encrypted with a secret key you don't have. So this is going to be something that you can use to check that your individual ballot was counted correctly, but that can't be used to prove to anyone else how you voted. We're also going to have to change the way that the election results are posted. Instead of publishing in the newspaper the way everyone voted, we're going to replace those voter choices with the same kind of encrypted form of each person's ballot. So now you have a way to check your result and to check that it's actually been incorporated into the count. The first thing you can check is that the election total is correct. And so the way this happens is that you can take all of those encrypted ballots that were published in the paper and perform a mathematical proof that shows that they add up to whatever totals have been announced on Election Day. I'll show you a bit about how that works later. But now any voter who cares to do so can A, check that their own encrypted ballots are listed in the totals, can check that the other voters whose names appear there are legitimate voters, the officials haven't just made up people along with their votes, and they can check the mathematical proof of the correctness of the tally. So these things together provide you with very strong evidence that the election outcome was correct, and you can do these without having to trust that the people performing the counts were doing their jobs correctly or that they're fundamentally honest. So this is the promise of E-to-E verifiable systems. So one neat thing about E-to-E is that it won't necessarily change what voters have to do. Voter participation is fundamentally optional. Voters can use their receipts to check that their results are properly recorded, or they can just throw their receipts in the trash. If enough voters check, however, this is like a form of distributed audit, and any large fraud is extremely likely to be caught. The other thing that voters can do is try to verify the accuracy of that mathematical proof that the announced totals match the published receipts or the encrypted votes. They can either verify the accuracy using an application that they wrote themselves, because the cryptography is all publicly described, or they can download applications to do this from a source that they trust, or they can just believe verifications that are done and published by political parties or other institutions they trust, or they can just do what they do now, accept the results without question. So this sounds great. Potentially this would be a huge security advantage, but there are lots of details we have to get right. Two of the most important questions are, how do voters know that these receipts they get actually match their choices? They could just be random numbers that have been made up, or encryptions of some other vote. The second question is, how are voters supposed to be convinced that the published encrypted votes actually correspond to the announced tallies? How does that process of the mathematical proof work, and is it going to be convincing for voters? So here's one way an E-to-E system could convince you that that encrypted receipt actually matches the choices on your ballot. So let's say you're at the polls and you're about to cast your ballot. You've already filled it out and you've received a receipt that's allegedly the encryption of your ballot. This kind of scheme would give you a choice. You can either cast the ballot then and there and accept that the receipt is correct, or you can challenge the receipt. If you cast, your ballot will go into the box. If you challenge, then the election officials will have to decrypt that encrypted ballot and show you that it actually matches your choices. So in this way, you can repeat this challenge process as many times as you want until you're satisfied. If at any point you open it up and you find that it's not your intended vote, then that's evidence that the system was trying to cheat, and we can proceed to investigate and find the cause. So end-to-end systems have been a subject of research for many years now, but only in the past few years have they started to emerge from the laboratory and be something that's been tested in actual practice. Probably the system that's gotten the most use and most real-world experience is one called Scantegrity. Scantegrity is an end-to-end verifiable voting system that is used with optical scan paper ballots of the type we're all familiar with. It involves just a few changes to the process from the voter's perspective. First, you're given a ballot that has bubbles that are pre-printed with verification codes written in invisible ink. You use a special pen to cast your vote and mark the bubbles. And when you mark a bubble, you're given a short alphanumeric code that corresponds to each choice you made. The voter gets to write these codes down together with the serial number of the ballot, and that forms their cryptographic receipt. Then after the election, voters can go online and use a website to verify that their receipt matches the ballot that's been recorded, and they can verify later through a public audit process that all of the other votes were totaled up correctly and match the official tallies. Scantegrity is great because it's just a fairly simple addition to existing optical scan balloting, but it provides these end-to-end verifiable properties for voters who would like to take advantage of them. And if enough voters do, that strengthens the process for everyone because it's like another form of distributed audit. Scantegrity has been tested now in 2 real elections for public office, both in Tacoma Park, Maryland, in 2009 and then in 2011. The researchers learned a lot from these processes and have gone back to the lab in hopes of perfecting the system and making it something that's broadly usable in other places as well. Another E2E system that's recently emerged from the lab is a system called Helios. And unlike Scantegrity, Helios is designed for online elections. Voters visit a website and fill out their ballot in a form in their browser. And then they're given a cryptographic receipt in the form of a block of text that they can copy out of the browser program. Voters can verify this receipt in several ways, either directly through the Helios website, or if they don't trust it, they can go to an independent website, or they can even implement the Helios software themselves and verify it that way. Helios has yet to be used in a binding election for public office. In fact, the creators of Helios say that it's nowhere near being ready to be used in real public elections. But it has been used in some large-scale private elections, including the election for the presidency of the International Association for Cryptographic Research. Helios raises some difficult questions. Is Internet voting using an end-to-end verifiable system something we can make secure? There are a number of attacks that you can imagine would be possible, including attacks on the user's client system. Malware on the client could interfere both with vote casting and with vote verification. So unless users verify their vote on a separate uninfected device, the malware could change the vote without being detected. Because of questions like this, it's difficult to be sure whether E2E voting will ever be something strong enough to provide actually secure Internet voting we can rely on. but it's likely that if internet voting is ever something we can secure, some technology like this will be a part of it. To give you a better sense of how E2E voting actually works, I'm going to show you a few more details about one of the systems and walk you through the process. So let's talk about Scantegrity. Before the election officials do a bunch of cryptography during a preparation phase. And among other things, what they do is they figure out what the verification codes are going to be on all of the ballots. This lets them print the ballots and prepare them. The codes are printed in invisible ink, so what the voter sees in the election booth is something like the middle image here. There's a serial number on the ballot, but all of the choices are blank until the voter actually votes using their special pen and reveals the invisible ink on the candidates they vote for. After voting, the voter can detach that little paper chit on the bottom of the ballot and write down the verification codes that showed up if they want. The piece of paper also has the ballot serial number printed on it, and the voter can later use this to look up their codes when the election results and cryptographic verification information are posted in public. Behind the scenes before the election, the election workers do other preparations too, and part of the process is that they run some software that's going to set up the system so that it can later be verified by voters. This part of the process is what makes possible that mathematical proof of the equivalence between the information that is published after the election and the tally results. The process is a little bit complicated, so I want to walk you through it in a slightly simplified version, but this will give you some idea of how that proof is constructed. During the preparation phase, the election officials run software that computes these three different tables. The table on the left shows for each ballot all of the different verification codes that would come up if the voter voted for each candidate. Now, the column order doesn't match the order of the candidates on the ballot. The different codes for a given ballot are shuffled around so that there's an added protection for voter secrecy. The table on the right is initially empty, but this will eventually show which choices voters have marked on ballots. The table in the middle establishes a correspondence between the entries in the left table and the right table. The column in the left in the middle table is a reference to one of the entries in the table on the left, and the column on the right in the middle of the middle table is a reference to one of the cells in the table on the right. But these are in permuted or shuffled order, so it's going to establish a kind of shuffling of the entries in the left table mapped onto the entries in the right table. Let's see what happens during counting. Let's suppose that the three ballots in this race voted for yes on the first ballot, no on the second, and no on the third. We can also suppose that these three confirmation codes circled in purple were the ones corresponding to those choices on the ballot. Now what we can do is we can follow the arrows that are mapping those circled choices through the middle table and onward to the right table. What we'll do in the middle table is mark an X in each row that is pointed to from a voter's choice on the left table. And then we'll follow the arrows to the right table and check off those boxes. Now the table on the right shows the results, 2 votes for no, 1 for yes, and we have our official count. So all of this is happening at election headquarters in software. None of this is being made available for anyone to see. So it's not public information yet. So let's see what's actually published in order to verify the election. So instead of revealing all of the entries in these tables, the election authorities start by only publishing encrypted versions. These are what are known as cryptographic commitments to most of the cells. Then they'll open up some of them. They'll open up in the confirmation code table on the left the table entries that are corresponding to confirmation codes for choices voters have actually made on their ballots, so the codes that voters took home. On the right, they'll open up the whole table, so everyone will be able to see which entries have been marked for which choice and be able to total that up and make sure it matches the tally. In the table in the middle, they'll reveal which entries have been marked with an X, but initially they won't reveal any of the left or right column entries, the things that tell you which entries in the left table correspond to which entries in the right one. So here comes the magic part. The election officials, after publishing this information, will pick a random number. Maybe, again, they'll choose something based on the stock market closing price on the appointed day of the audit. And based on this number, for each row in the middle table, they will decrypt and reveal either the encrypted value on the left or the encrypted value on the right. So here we'll decrypt in the first row the left value, the second one the right value, and so on. If they open the value on the left, this reveals the correspondence between that row and one of the confirmation codes in the left table. If they open the right one, it reveals the correspondence between the middle table and one of the entries in the right table. But there's no place where they're going to open and decrypt both of those values, and you'll be able to see a direct path from one of the confirmation codes to a voted choice. However, since these values were published after they were encrypted, there's no way that the election officials could go back and change what was in one of those encrypted envelopes after it was decided that it should be revealed. They're committed to them. And because of that, we can convince ourselves that all of the confirmation codes are accurately recorded. We can check on the left side that any of the voted codes for which the correspondence has been revealed actually maps to a row in the middle table that has an X, that is one that was supposed to be a choice marked by a voter. And we can also check that any of the non-revealed confirmation codes on the left for which the correspondence has been revealed maps to a row without an X. On the right half of the screen, we can verify that each of the correspondences also matches. If there is a correspondence that is not marked with an X, it's not marked with a check in the voted choice table. If it is marked with an X, there's a check in the voted choice table. So this is an example of what's called a cut-and-choose protocol, where we're either going to reveal some information or other information, but there's no way to tell in advance. So someone who is trying to cheat would, in order to look consistent after some of the information was revealed, would have to be extremely lucky. And we can make it arbitrarily hard for them by increasing the complexity of the system. It does get a little complicated, though, and I'm not even showing you the full detail, but this gives you some sense of how E2E would work. End-to-end verifiable voting has a tremendous amount of promise, but there's still several difficult questions about it. One has to do with the complexity. This isn't exactly simple stuff. And the question is, how much added burden is it going to add to election procedures and election official duties that are already considerably difficult given the scale and messiness of real elections? Is this going to be something that's simple enough to actually practice on a large scale? Another question has to do with usability. Is the process of end-to-end something that regular voters can follow what they're supposed to do and complete the steps correctly? How many voters are going to even bother to, say, write down the confirmation codes in Scantegrity? If the system isn't usable, then it's not going to be able to be verifiable either. Another question is comprehensibility, and I think this is the biggest issue of all with E2E. By comprehensibility, we mean the ability of voters to understand why their votes are being counted correctly. It seems like most E2E schemes, anyway, require quite a bit of knowledge and understanding to follow the intricacies of the procedures. We want, ideally, for voting systems to be something that non-experts can understand, that anyone can follow. And if it takes special cryptographic training to understand exactly why your vote is being secured, that's less than an ideal amount of transparency and comprehensibility. Finally, there are security questions, certainly about end-to-end voting if practiced as an internet voting scheme, but also about some of the offline traditional voting forms of E2E too. Researchers are still working to strengthen the proofs of security that are available for the different properties and to understand everything that could possibly go wrong. Despite these problems, I think end-to-end is one of the most exciting and most promising new technologies in election research, and I am confident that in some form, someday, this is going to be a widely used technology to strengthen the way we all vote.